go on and look at the property. We have two property. Linear maps can also be one-to-one, onto, and they can have both. Now, a linear map that is both is called an isomorphism. So if a linear map is both one-to-one and onto, then it's a correspondence, but then it's called an isomorphism. Because what's happening is iso means same, and morphism means sort of like shape. So it's the same shape. It means in some sense, if you have an isomorphism between two vector spaces, in some sense, they're the same space. Now, if it's not an isomorphism, if it's linear, then you call it a homomorphism, which means similar, but not the same. Okay, so same shape. So so that a homomorphism doesn't have to be one-to-one, doesn't have to be onto, it doesn't have to be either one. And these two kinds of maps, ones that are isomorphisms and ones that are linear but but not necessarily an isomorphism, each have different roles to play in linear algebra. This identifies vector spaces that are essentially the same. Essentially the same. The a map that's not one-to-one or onto is more like a microscope that that allows one to examine internal structure of a vector space. And also, now, what's going to happen is that there's going to be a connection between, this is sort of an overview, for every linear map can be represented via a matrix. So a matrix here, it implements a linear map. And every matrix implements a linear map. Every linear map can be represented by a matrix. So this is going to be the connection that where matrices play the central role, whereas before they've just played a secondary role, and we can then begin to interpret linear systems in the context of linear maps. Okay, and the properties that we had of vector spaces, like the kernel, the null space, the rank, all of the rank, and we haven't defined the terms I just mentioned, but the kernel, the not the kernel, the dimension of matrices will reappear, and bases. So the two things we did before will come in here: the dimension of vector spaces and bases. Okay, so all the stuff we've done in the last bit will reappear here. Okay, well, that's sort of an overview. And the question is then to look at how can I show that or verify or detect whether, so here's the task here. Identify or verify that a linear map is one-to-one and or onto. So let's do say one-to-one. Well, here's the let's look at our map before. We had the map F that took X, Y, Z, and it went to X plus Y and Y plus Z. And we can ask, well, is this map one-to-one? Okay. And well, so there's two possibilities. If it is not one-to-one, you want to find a counterexample. But if it is one-to-one, you need to prove it is for everything. Now, this goes back to those formal properties. What the formal property for being one-to-one said is if two codomain elements are the same. So we need two. So let's look at this. For every V1 and V2 member of R3C, right? For every two vectors, we have to have that if F of V1 equals F of V2. If they're the same, then V1 equals V2. Okay? And because this says, okay, if the two images are the same, it rules out the situation where you have V1, V2 going to the same vector. It rules out this one here. Let me see, make sure I'm actually, okay, good. Okay, so now how can we given a concrete map, how can we verify that this map is one-to-one or not one-to-one? Well, we can take two vectors, V1 and V2, right? X1, Y1, Z1, there's V1. Here's the second vector, which has two different sets of components. And then we can form F of V1 here, right? And F of V2. So we can say, okay, well, we want to look at this condition here. We want to sort of check, let's suppose F of V1 equals F of V2, because to check whether it's one-to-one is to check one-to-one is to check whether this conditional, this P implies Q, is true. Well, the way we show that this is true is by supposing that this is true, the condition is true, and then showing that this is true. So what we have to do is we have to suppose that this is true. Well, for these vectors, that is, we're supposing that x1 plus y1, y1 plus z1 equals x2 plus y2, y2 plus z2. So we're supposing this. Now you notice what that, you can see directly what it is you take this image here, choose two of them and set them equal. Now what we have to show is need to show that x1 equals x2 and y1 equals y2 and z1 equals z2. Okay? Well, if we look at this is really, we can write this out as a linear system and say, well, if these are equal, then x1 plus y1 has to equal x2 plus y2 and y2 plus y1 and y1 plus z1 has to equal y2 plus z2. Okay, well, this is actually a linear system, but not written in the regular way. It's a linear system in lots of variables, right? So um, let's see how to rewrite this. Okay, well, we could write this as the first equation is x1 plus y1 minus x2 minus y2 equals 0. And the second one would be y1 plus z1 um, minus y2 minus z2 equals 0. Okay, so here we have a linear system, and we could write the augmented matrix for this as 1 1 0 minus 1 minus 1 0 and 0 1 1 0 minus 1 minus 1 0 0. And you can see right away that this um, is in echelon form, already in echelon form. And so we would see that x1 and y1 are, now what do we have to show? This is sort of the x1 column, the y1, the z1. We would have to show that this is a system for x1, y1, z1, and z2. But these are, and you can see that this is going to fail to be. We can solve for y1 in terms of z1, z2, and y2 and z2, and then x1 in terms of these variables. And we're going to be able to choose y2 and z2 freely, so they're not equal. So we can see right away that this one is not going to, it'll be easier to see what the point of this system is when we do one where you can show that it's one-to-one. So this one is not going to be one-to-one. And because of the fact that we needed to show, say, that y1 was equal to y2, but y2 is a free variable and y1 is a leading variable. So this last equation here would be y1 equals y2 plus z2 minus z1. Well, we can choose, say, since z1 and z2 are free variables, we could choose, say, z1 to be 0 and z2 to be 1, and then y1 would not equal y2, and z1 would not equal z2, so it's an example of and we can freely choose y2. We could choose this to be 0, so this would be 1, and then we could plug that in here and find, say, that if y2 is 0 and y1 is 1, we could choose x2 to equal 1, in which case x1 is going to equal 0, and then we can say this is an example of two vectors that have the same image. These are two different vectors. Like I can choose basically x1, x2, these three differently than these three, and the images then will not be one-to-one. And you can see this right away that, like, for example, I could choose, because this is a sum here, I could choose here this to be 1 and 1. So this is 2, but I could also, I could choose, say, z and y to be anything, but then I could choose x and y. I could choose z to be minus y, so this would always be 0 here. And then I could choose X plus Y to be 1 plus 1 is 2, and then or 2 plus 0 would be 2. So I can form 2 0 many different ways. So this is not, so this map F here is not 1 to 1. So that maybe that's not completely satisfying because it seemed too easy here for this map to see. This is massively not 1 to 1. So maybe we need a map that is 1 to 1. So let's do another example of that. Another example. But let me stop and ask if you guys have any questions.